So I'm going to talk to you guys about circuits. That's the title of my talk. What are circuits? Circuits are like streams, and streams are like circuits. And they both represent the notion of something that receives a value and can emit a value. So this yellow box here is the construct. The red arrow is whatever input it can receive. The blue arrow is whatever output it emits. Um, so if you're lying down at the moment, this talk may put you to sleep. So if you could sit up, if you want to listen. Otherwise, just go to sleep. You know, it's cool. I know it's second day. I was out last night too. So, and plus, as you're sleeping, the mind is vulnerable and I can just say anything I want. Uh, so, how I started down this track of exploring circuits was through asynchronous functions. So I do a lot of JavaScript programming where I have to wait on something to, to, to basically happen before I can act on it. So how this is represented in Node is through a callback, where you have the first parameter being an error and the second the result, right? So everyone knows you have a function foo, it does something, calls back, and then you do stuff with whatever the result is. Is that clear? Some guy's face is like, he doesn't understand this. But if you don't understand this, this is going to be tough because this is like the very basic thing. Um, if you want to use foo with another asynchronous function, bar, you got to nest them, right? So use foo, calls back into bar, and then you pass it another callback, and then you finally do stuff with both the results. I mean, it's quite simple. However, I wasn't really happy with this because if you have to keep composing asynchronous functions together with other asynchronous functions with other asynchronous functions, then what happens after a while is you get callback hell. And everyone's familiar with that, right? It's like when your code is moving off the side of your screen, it's also really hard to sort of follow. So callback hell, I talked about callback hell in LXJS, and some people said basically that they had never experienced it. So I was really surprised because this is sort of one of the patterns that you first encounter when you start with JavaScript. So I looked into it. I was like, well, maybe this might be something, a phenomenon that only I'm experiencing. So I looked at the top 10 node categories, and the control flow async goodies, that's a sizable chunk. It's a third of the size of the size of web frameworks, which is like the top module category. So control flow goodies, what are they exactly? I was looking at NPM, and the third most dependent upon module is async. So if you're not familiar with async, async is a utility module which provides straightforward, powerful functions for working with asynchronous JavaScript. So I just got that from the README, right? So other people are experiencing callback hell as well. That's why there are so many modules around that try to tackle asynchronous control flow. So I think hell is real. Callback hell is real. So I mean, if you're experiencing this, then this talk will be interesting for you because you'll have like a lot of. I'm going to try to give you like some other ideas about control flow. So one of them is streams, and I think James talks a lot about streams, but I want to give you some other ones too, taken from category theory and functional reactive programming and all that good stuff. So right. So I want to start with drag and drop. So this is how to create a drag and drop behavior, just using normal JavaScript with a bit of jQuery in there because it's a good piece of sugar. So basically, you have a function move. It takes a down event and a mouse move event, and then it updates your the DOM element style. That should be pretty straightforward. So now in the drag and drop function, it takes a DOM element, it waits for a mouse down, and then it waits for a mouse move, calls move each time mouse move is emitted, and on mouse up, it kills all the callbacks, right? So we can actually test this out. Um, so right here, I pretty much can you is the screen shared? So can you I don't know how much bigger this can go. But I mean, it's exactly the same code, right? So if I run that, you can see, you know, I can drag this thing. So you just have to trust me. I can even paste it for you, but you know what? I'm not going to do that. You're just going to have to trust me. So that is exactly the same code that's in the JS fiddle, and it's pretty succinct. If you've ever tried to program like if code drag and drop behavior before, I mean, I don't know if you can get it down smaller than that. Maybe we can like take off this mouse down event actually, but so if we think of it as as a state machine, this is how it might look. We have like two states. One is idle and the other is dragging, and you move between the states via mouse down or mouse up. So how might this look with async, since you know that's the module that everyone uses for asynchronous control flow? So you represent the first state, Q0, with by just waiting for a mouse down event. And then when that gets called, it moves to the second state, Q1, which waits for a mouse move event. So this should be pretty straightforward. So what's happened here is like instead of having everything together, like in the same drag and drop function body, I've basically just separated it out into two states. One is idle and one is dragging. So this is how it would look when composed together. So the big thing about this is what you're doing is you don't have that nesting that happens with the normal callback, like nesting callbacks. But what you do lose is maybe like how if we didn't have async, we might have to compose them in a different way that hides the execution flow of each of the callback handlers. But async sort of allows us to grab them together and sort of describe them in one place. Drag and drop is a waterfall of Q0 and Q1. Mouse down and drag. Everyone's like going, but you get it? It's so awesome, right? Okay, so if we look at both of the code, like both of these pieces of code side by side, you can see that the vanilla JavaScript is pretty, I mean, it's pretty readable. Async sort of clutters it up a bit. But we're allowed to separate the states Q0 and Q1, which sort of, it lets us do other things with them. For example, if we wanted to reuse Q0 for something else, like a mouse down, something else is waiting for a mouse down, we can use that. So it's modular. However, it does sort of like make the code a little bit, it's sort of fatter right now, the async code. So Michael said JavaScript is done, like in LXJS. I mean, paraphrase, I wasn't actually there. But Brian McKenna tweeted something like this. The language is done, JavaScript is it. And you know what? Maybe that's true, because I mean, if we just wanted to do drag and drop, why would we have this async module that clutters up our code, allows us to separate the states? It makes it more modular, but what if we don't ever want to use Q0 or Q1 just independently? It sort of doesn't need to be done, so why do it, right? So this is sort of like the important point of this talk. So Michael says, you know, there's a point where something is good enough, and we move on to more important, higher order things. And I think that's really important here. Like, some people use JavaScript for a set of problems, and JavaScript is totally good enough for that. Why change anything? It's solved my problem, right? But then there's a lot of other people, I guess, who, for them, JavaScript isn't good enough. There's always like, there's something that they do every day that JavaScript just sort of falls short of a little bit. So this talk is for those people. Basically, this is an advanced topic, and I'm not going to tell you whether to use one method or another. That's something that you have to judge for yourself. You know, I'm just going to give you some tools, and then you can decide if that tool is good for what you're doing. Sound good? All right. So everyone's familiar with streams. Or at least I think so. After James's talk, pretty much I've heard streams until like it's coming out of my ears. Like I was at LXJS and I saw so many stream demos. But I'm going to give you a stream demo just to like really nail that right in. So if we turn this drag and drop problem, this state machine, into a stream, how might that look? So I've got this piece of code there. We have a readable stream that basically emits we've encapsulated the whole mouse down, mouse move state machine, and it only emits, what does it emit? It only emits mouse move events. In fact, it emits it in pairs of a down event and a move event, because we need the down event to sort of offset where we're going to change the coordinates of that element. So it's a little cluttered, but you can sort of see that it's very similar to the vanilla JavaScript. It just sort of like hides that, and it only emits it in the stream now. You can see that this rs emit part, right here. I can't highlight it, but you can see the, can I use this thing? Nope. I don't know what this laser pointer is here for. It's not really of any use. But so I use this thing called bind. I don't know if everyone uses bind, but it's basically a partial application of some parameters. So it's really just the same as having mouse move receive a callback that calls rs.emit with data e0, which is from the mouse down event, and then gets past the mouse move event, which would be e1. And then we end up sending e0 and e1 into the move function, which earlier we defined as it just moves the thing, it updates the xy coordinates. So this is how drag and drop would look as a stream. So remember, we looked at it as just jQuery code, just JavaScript, and then we looked at it as an async waterfall, and it looked a little different. We got some different semantics out of it. We got to separate the states into Q0 and Q1. And now we're looking at it as a stream, and I don't really know how to assess this. It's just kind of cool. It's a stream. We can even streamify the move function and pipe mouse events into the move function, so that every time it emits something, it just moves. So that's kind of neat, like thinking of some sort of emitter of events getting piped into just a normal function. Except I couldn't really do that. Streams. So the thing with streams is it's a little weird. You can call rs emit data, and you can pass it any number of arguments, but somewhere in the stream code, and I mean I can show you this gist. You know what, it's not important. But somewhere in the stream code, it only passes like one argument. I hope someone fixes that. So right now I have to like wrap it just in like a pair, a tuple, and then I can, so I have to change the move function here. So what would be handy if I didn't have to change the move function is that I could just, use the same function with any kind of control flow construct, whether it was a waterfall, whether it was jQuery, whether it was a stream. I could just use move with like down event and mouse move event, but until that changes. So what we have here is we can see the stream as a pipe between two processes. One is something that emits, and the other is something that receives. And I drew boxes around them because, so basically the state machine here, it's separated, right? And what streams allows us to do is it allows us to use anything that is readable and smush it together with anything that is writable. And we don't need to think about what's actually inside the boxes. And that's something that's really cool. You know, because it's very, so I don't remember whose talk it was, but someone was talking about how when you have a really heavy framework, like a plugin system, everything has to follow this same, everything has to like identify itself as a plugin. And sometimes the interface can be really heavyweight, but Streams interface is really quite simple. So a lot of things can be streams, and as you can see, like to make something into a stream, it's not super heavyweight. You know, you just you just instantiate a stream, declare it like set it to be writable or readable, and then just start emitting things. So the interface is really simple. Streams. What do we get for free? We really get this pipe for free. So if we streamify whatever components we're using in our control flow, we get the pipe for free. And this is really important because pipes are kind of they're kind of like a composition operator, right? So it allows you to compose two streams together into one, and the result of that is itself a stream, and then you can use that in other streams. And so the whole lure of streams and pipes and compositions is that you get like this really you get to I switched the slide too early. This has nothing to do with what I'm talking about right now, but but hey, it's a burrito. So what you get is like what I like to think of a piece of code is basically a composition of just different bits smushed together, right? So everything can exist independently, like a function or an object or whatever, and depending on how it's composed together is what makes a program different. So pipe is a sequential, it basically sequences things. You have the first thing sequenced with the second thing. A pipes to B. That means something has to go through A to get to B. And that's just a really simple combinator. The pipe is a sequencing combinator. There are so many other ones out there, and this is what I'm going to try to tell you guys today. So let's say you have this thing called M, right? And it has just two things, right? So a stream, it has, what's a stream? It emits something, or you have a write function so that it can receive something, right? So that's the interface of a stream. So the interface of this particular construct that I'm showing you now, M, A, you have two functions. So you have a then, which is also a sequencing combinator, and then you have a unit. So what the then does is something very similar to what the pipe does. It takes one kind of this MA, takes another MB, it just smushes them together. This unit function takes some raw value, and then it puts it into the context of M. So if you think of this as a stream, actually, is that? No. Let's start with a list, because everyone's familiar with lists, right? So a list is of a type MA. The then function, you can basically, it takes a function, and then it basically like runs this function on each of its, you know what, have you ever like written some code and come back to it and not understood what the fuck it meant? This is what I'm experiencing now, but it totally works. I promise you. So let's look at unit, because unit is pretty, it's pretty simple. It's much more simple than the then combinator for list. But basically, you pass it an X, so it could be a number, it could be like 1, it could be A, it could be a string, and then it just puts it inside of a list. The context M, right? So remember, unit takes a raw value and it puts it inside of a context. And that's exactly what this is for the list. The then function, I think what it does is it takes many lists, and like if you take two lists and then you put them together, it basically like concatenates the whole thing, plus there's a mapping function. So that's what it's doing there. The idea of a continuation, so this is like an asynchronous function. So this can capture asynchronous functions. It takes two asynchronous functions, and then it it sequences them. So it calls the first one first, foo, and then bar. If we pass in foo and bar into here, it would give us another asynchronous function that would be called back after bar was completed. And the unit definition here is to take some x and then put it inside of a callback, so that when you call that thing, when you call this function and pass it a callback, it just gives x back to you. So that's the context here. Now, streams, we're familiar with streams. How may streams look as a type MA? What we have is we create a stream that basically emits data when this is actually, it's again, this is confounding me. But it basically emits data based on what's happening in the two streams that it's supposed to compose together. The unit basically is a singleton, and it just emits like 1x. So you can see the stream really as maybe kind of a list, right? So it's a container for values. And that's exactly what this MA thing is. It can capture containers like lists or streams, but it can also capture computations like asynchronous functions. So what do we get with this, right? So if we have an object and we implement then and unit, what do we get for free? Well, for instance, we can get this function chaining thing that I wrote that's sort of totally ripped off Fab.js, but whatever. It's really cool. It's sort of a way to look at, let's say if this was an asynchronous, let's say it wasn't stream, it was like, I showed this like demo in LXJS and it had a cont operator, an asynchronous function thing to it. So but it's exactly the same API. So we have a stream that we emit rabbit. Basically, we emit rabbit, we store it in X, and then we call generation on it. You know, you're just gonna have to trust me that it does what I'm saying it does. And when we run this app, it basically like, oh, I didn't define generation here, but generation is basically a replicate function with a partially applied 3 to it. So it just returns 3 rabbits. And you know, you can keep on doing this and it'll return 6 rabbits or 9 rabbits or whatever. So, but what I want to show you here is you get this function chaining API for free that you can use with a stream, with a cont, or with a list. And it doesn't matter like which kind of thing it is, because it's just a general MA construct that this function chaining can work with all of them. So that might not be the biggest selling point, but I'm just telling you, right, that again, this is one way to compose asynchronous functions and other kinds of control flow. And you decide whether it's the right tool for you. So if we go back to comparing the vanilla and the async style of code, how might this look as a continuation with function chaining? So what we can do is, again, we have the move function, which is just like a normal function. It takes a down event and a mouse event, and then it updates the DOM element. And we have 2 states, mouse down and drag. So what we see down here in the drag and drop, the execution flow, is that it looks pretty sequential. Like the first thing that gets called is the mouse down, and then after that gets called, it's just drag. And then you can actually keep looping that. I don't know if I have that combinator here, but basically there's this thing that, there's this function that I had forever that takes any kind of MA construct, and then it can join it to the top of it again. So it's sort of like if you wanted to run something forever, it could take the end, the last operation, and then after the last operation, it goes back to the top operation again. So it's kind of like a looping construct for any sort of MA. So I did want to talk about another kind of construct. It's called ABC, really. Actually, it's not called ABC. It's called an arrow. But it has 3 parts to it. One is the context. The other is some sort of notion of input. And C is some notion of output. So what kinds of things follow this pattern? A function follows this pattern. A function receives some kind of input. It gets applied to it, and then it returns some sort of value, C. Streams do this too. I mean, bidirectional streams do. You can write something to a stream, and then that same stream can emit a value. So in JavaScript, I mean, we don't really care about types so much, though it's becoming more and more something we care about. It's actually something that can receive anything and it can emit anything. Streams as one of these ABC constructs as an arrow. Basically, you need to define two things. Actually, it's three things. Yeah, three things. R, dot, and first. So you can see visually what happens here. The R function takes any function, right? And then it creates a conveyor belt out of it. So those squares next to the F, think of it as like a belt moving from left to right. So as each item comes through on the left, it calls that function, and then the value that's emitted gets pushed down the belt. You can connect two of these arrows together with this combining operation, dot. And what you can do is if you can, there's also this notion of like pairs. So you get basically a conveyor belt that works on pairs. So first basically works on the first item of a tuple and doesn't do anything to the second item. So this is pretty abstract. So what can you actually do with this, right? I don't know if you want to go through the. You could probably look at that later, but it's pretty interesting. What can you do with that? Well, you can. There's something called functional reactive programming. That's sort of like. There's a lot of interest for it in the Haskell community because functional reactive programming with this sort of arrow combinator thing is a pretty like intuitive way of thinking about streams of data and events and things like that. And I want to show you how it works, but I actually didn't get to finishing the demo. But I'll show you I'll show you what I got with just plain JavaScript. If I can. Oh, we're not gonna see this. What? Control Shift up? What does that do? Oh, no way. Okay, I did it, but Control Shift. You know what? It's not gonna work, but it was like a pretty sweet sort of broken game of Pong. Why isn't it working? That's weird. Well, just come over and I'll show it to you guys, like if you want to see it. But basically, we have actually let's just look at the code. So this isn't happening. This fiddle's dead. Okay, back to this. So basically, what these arrow combinators allow you to do is express something kind of like a graph, which is sort of what like the big win is, except I couldn't show you concretely, but you'll have to use your imagination, which shouldn't be that hard, I hope. We just started from the start again. But, okay, wow, that was lucky. So if you think of like the first thing that triggers all of these things, it's like a game tick. So for this piece of code, it was request animation frame. So the tick basically emits a value to key and ball position, right? And these things emit their own values because they're streams. Player pause and ball pause, they get paired into like one of those like conveyor belt things, like in first. And then they get sent into this render function, which basically is just a normal function that will draw the rectangles on the screen. So I did want to show you how that would look in code. Actually, no, I do have a thing right here. So one way to do it is with the fan-out combinator. So remember when we, so I said R, connect, and first. If you implement those things, you get other things for free, just like in streams. If you create a stream, what do you get for free? You get the pipe combinator. If you instantiate something as an arrow, you get a whole different bunch of combinators like fan out, fan in. And we can even do something crazy like that fab.js function chaining and express the execution flow of the game like that. Except whoever wants to see it in action, just come over after. But basically, this is what I want you guys to take away from this is that streams, yes, they're a great abstraction. But don't just stop there. Like, streams give you pipes. Pipes are great. Keep on going. Like, look for other abstractions. There's, I mean, so it's sort of like a thinly veiled thing here, but like the MA construct is from category theory. It's a monad, and the ABC construct is an arrow, and they adequately these things capture certain control flow things that JavaScript programmers face all the time. It's just they haven't. I don't know. People just are scared of monads or something like that, but don't be. You saw exactly how much lines of code it took to instantiate something as a monad. It wasn't a whole lot. So basically, yes, abstractions are great. Go and like don't stop discovering other abstractions that may be great tools for what you're doing. Keep on like learning, and streams are great, but just look forward from there. Did I just? All right. And these are the I'm gonna publish these slides, but all the JS fiddles are on these links, and here's the attributions. But I hope you took something away from this. My name is Neuman Vong, and I'll stay for questions. Thank you.
Thank you. Any questions?
There's one guy at the front. It's always the guys at the front.
How would you compare this kind of like using any of these approaches for async programming to like using something like deferreds and promises?
So deferreds and I think there for each use case, deferreds. There could be use cases where deferreds and promises may work really well. You just have to go and experiment with them. Like jQuery uses deferreds internally, and I think it works really well for. I don't know. I guess it works kind of well. Has anyone used deferreds? I haven't personally used deferreds, but I mean, there's the overhead of the abstraction, right? I guess it does make things more modular. Anytime you separate out the states and not have these nested callbacks, you make your solution more modular, and you can change it and reuse certain things that you wouldn't otherwise be able to do. So I think streams are good. I think deferreds are good. Don't stop there. Like again, like there are other other disciplines that have researched and tried to solve these problems for a very, very long time before JavaScript. So, I think it would be good if everyone that was using streams, everyone was using deferreds, had to look at some category theory principles as well. So I don't know if that answers your question, but they're just another tool in the toolbox. Yeah.
Great.
Okay.
Okay, thank you, Neuman.